In this video, we're going to continue working with exponential and logarithmic functions, but now we're going to use them to model real-world situations. So this, of course, means we're going to have lots of word problems in this video. And we're going to need all of the skills we've learned in the past few videos, how to deal with logarithms and exponentials, how to solve exponential equations and logarithmic equations, all of that. So let's begin by not quite having word problems yet, but just practicing solving different equations for different variables. So just a quick example as a warm-up. Given the equation t equals 78 plus 272 e to the negative kt, solve for k. So notice we have three different variables in this problem. We have capital T, little t, and k. And my goal is to get k completely by itself. So don't worry about having all those variables. Just treat them like they're numbers, and we'll get to the point that we need to. So if I have t equals 78 plus 272 e to the negative kt, this is an exponential equation, and we know from our last video we need to get the exponential term by itself. So I'm going to start by subtracting 78 from both sides of the equation. So now I have t minus 78 equals 272 e to the negative kt. And so my exponential term is not by itself quite yet. I now have to divide by 272. So I'm going to get t minus 78 over 272 equals e to the negative kt. Now that the exponential term is by itself, I'm ready to take logarithms of both sides. And I'm going to use a natural logarithm. So I get the natural log of t minus 78 over 272 equals the natural log of e to the negative kt. Now remember that when you have a logarithm and an exponential of the same base, they undo each other. So this right-hand side is now just equal to negative kt. And I still have all of this mess over on the left side. Well, now I have just one step left to get k completely by itself, and that's to divide by negative t. So if I divide both sides of my equation by negative t, I'm going to get natural log of t minus 78 over 272 divided by negative t is equal to k. And I would put a box around my answer right there, though yes, you can write this in different ways by using properties of logarithms. I personally would just stop right there. All right, so that's how we solve an exponential equation for a particular variable. Now let's solve a logarithmic equation for a particular variable. These skills are going to come in handy once we get to our word problems. So next example, given s equals 90 minus 20 natural log of t plus 1, solve for t. So this one only has two variables, capital S and little t. And the first thing that we're going to have to do with this equation is get the natural log term completely by itself. So I'm going to start by subtracting 90 from both sides. Now, my natural log is still not by itself. It's being multiplied by a negative 20. So I need to divide both sides by negative 20. And now I'm ready to solve the equation. So I have a logarithm by itself on one side and a bunch of stuff on the other side. We have to rewrite this in exponential form. the base of that logarithm is e. So I get e to the other side of the equation equals t plus 1. And so to get t completely by itself, I just have to subtract 1. So I get e to the s minus 90 divided by negative 20 power minus 1. And we're going to get a lot of ugly answers. That's very normal on here, so don't freak out if you get an answer that's not perfect looking. You're going to get ugly things when working with equations like this. So our first example of using these types of equations to model real-world situations, we're going to talk about exponential growth and decay models. So our exponential growth and decay models look like y equals y0 times e to the kt power. And if that k happens to be a positive number, this is exponential growth. And if k happens to be a negative number, this is exponential decay. And these formulas, sometimes they use different variables, not just y and y0. Sometimes you'll see an a or a p or a p0, lots of different things, but they're all the same type of equation. All of these equations of this form are called exponential growth or exponential decay models. They can be used for a lot of different things, including compounding interest. You might recognize this is the same thing as a equals p to the rt. Just some things are named a little bit different. So we've already done like compounding interest, which this can be used for. This can be used for population growth. If it's decay, we're talking radioactive decay, things like that. And we're going to start with a compound interest problem, but it's going to be a little different than the ones we did in the previous video. So an example. We are going to suppose that $10,000 is invested and at the end of 5 years, the value of the account is $13,771.28. Use A equals PE to the RT to determine the average rate of return R under continuous compounding. So notice this A equals PE to the RT, this is an exponential growth problem. That's that same form we just talked about, just with different variables being the placeholders. Now, we have to figure out what stuff we're plugging into each piece to solve for our R, which is our interest rate. So when I look at this problem, the first number I come across is 10,000. And where would that 10,000 go? Well, remember from when we talked about this before, what we put in this P spot is the original amount that we're investing. So this 10,000, that is P. The next number I come across is this 5 years. That's talking about time, so that's T. And then this $13,771.28. Well, it's not my R, that would be my interest rate. It's the amount in my account, So that goes on the other side as A. So now that I know where everything goes, we just put everything in the right places, and then we have to solve for the rate R. So let's get it set up. I'm going to rewrite the equation without the stuff plugged in. But now I'm going to put the stuff where it's supposed to go. So I have my 13,771.28 as A. My P was 10,000. Then I have e to the r times 5. And I want to solve this for my r. This is just an exponential equation, and we know how to solve those. First, we have to get the exponential term by itself. So I need to divide both sides by 10,000. If I divide 13,771.28 by 10,000, I get 1.377128. And now I have that decimal equals e to the 5r. Now we can take a natural log of both sides. And remember that when you have a logarithm and an exponential of the same base, they undo each other. So this natural log of e to the 5r is just 5r. And I still have natural log of 1.377128 on the left side. So to get my r, I just have to divide by 5. So my interest rate r is natural log of 1.377128 over 5. That's the exact answer. But we know in the real world, you're not going to go and invest money in accounts and have them tell you that the interest rate is natural log of 1.377128 divided by 5. No one talks like that in real life. So let's actually type this in the calculator and see what we get. You would get about 0.064, and it's a decimal that goes on forever. And the way that this is usually reported on investments is as a percentage. So this 0.064 as a percentage is about 6.4%. That is how they would likely tell you the interest rate in real life. All right, so that wasn't too bad. It's still the same exact thing. Even though it's in a word problem format, our techniques for solving have not changed. Let's do another example of exponential growth. This time we're going to use a population problem. So an example. On January 1st of the year 2000, the population of Texas was about 21 million. On January 1st, 2010, the population was 25.2 million. Part A. Write a function that looks like P of t equals P0 e to the kt to represent the population of Texas t years after January 1st, 2000. And we're going to round our k to 5 decimal places. All right, so notice this equation that they want us to use to represent the population. It's yet another exponential growth equation. It's still in the same form. It looks like our compounding interest, just with slightly different variable names. So first thing we should do is figure out where everything is supposed to go. On January 1st, 2000, our population of Texas is 21 million. And we're going to be talking about years after January 1st, 2000. That means this 21 million, which was my population in 2000, that's my initial population, P0. Then this 25.2 million will go on the other side of the equation in the P of T spot. And what's my T value? Well, I get that from this date. January 1st, 2010 is T equals 10 years after January 1st, 2000. So I'm gonna have 25.2 million on the left side. My P0 is 21 million, e to the k times 10. The first thing we're gonna have to do is figure out what k is, and then we can write our generic formula. Now I'm going to write this so that I'm not going to write all of the zeros to make it millions. I'm just going to know that my populations are talking about millions. So here's what the form of the equation is supposed to look like. And we know that once we figure out what k is, we're going to look like P of T equals that initial population, which was 21 million, e to the kt. So I have to plug in that other information that we already figured out what those variables are supposed to be to solve for k. And then once I have k, I'll put it back into this form right here to represent my population. So we have that 25.2 was the population after 10 years. So I've plugged in the 25.2 and the 10 into their appropriate places. This is an equation I can solve for k. Start by dividing by 21 to get 1.2 equals e to the 10k. Take a natural log of both sides. And then that natural log of e to the 10k is just 10k. So I get natural log of 1.2 equals 10k, which means my k is exactly equal to natural log of 1.2 over 10. But the problem said to round k to 5 decimal places. If you type that into a calculator, you'll get our k is approximately 0.01823. So we found our k, but what the problem wanted was a function to represent the population. That function is our P of T equals our initial population of 21 million, e to this k times t. Now this function here, I can now take any value for t that I want and plug it in, and it will tell me what the population of Texas is predicted to be in that particular year. So that's our part A. Now what do we do for part B? Part B says predict the population on January 1st, 2020 to 1 decimal place. So to figure out the population on January 1st, 2020, I have to plug something in for my t. We just have to figure out what that value is. Remember, t is talking about the number of years since January 1st, 2000. So this would be t equals 20. And then all I have to do is type all that mess into my calculator, and it will tell me what the population is predicted to be. So that's a lot to type in all at once. So sometimes I like to just type the exponent in first, and I see that exponent simplifies to 0.3646, and then I type this in to get about 30.2. And remember, we're talking about population in millions. So this just says that if it continued to grow at that same rate, the population of Texas would be about 30.2 million by January 1st, 2020. Now, part C, we get to use our same function in a different way. Part C says, in what year will Texas reach 40 million? So this time we know what the left side of the equation is. It's 40. We want to figure out what t is to make this into 40 million people. So well, let me write down my whole function again. P of t equals 21 e to the 0.01823 t. And I know my p of t we want to be 40 million people. So I want to solve this for t. Well, this is just an exponential equation, and we know how to solve those. Start by dividing both sides by 21. I get 40 over 21 equals e to the 0.01823 t. Now I can take a natural log of both sides and get natural log of 40 over 21 equals natural log of e to the 0.01823 t. And then we know that that right-hand side simplifies because natural logs and exponentials with base e are inverses of each other. So now all I have to do to get t by itself is divide by that decimal. So I get natural log of 40 over 21 divided by 0.01823 is equal to t. Now, of course, that doesn't help us very much because we want to know what year this is. Well, that's a really strange way of saying what a year is. So you would type it in your calculator, and we get that t is approximately 35.35. So now we have to remember what t represents. T is the number of years since January 1st of 2000. So having t equal 35.35 means that we're somewhere in the year 2035. Partway through that year, the population will reach our 40 million. All right. Now we're going to talk about how to write an exponential expression using base e if you don't have base e to begin with. If we let t and b be real numbers, with b greater than 0 and not equal to 1, then b to the t power is exactly the same thing as e to the natural log of b times t. So this gives us a way to rewrite a problem. If it doesn't have e as the base, this allows us to rewrite it that way if we happen to prefer using that base. Let's do an example where we rewrite using e for our base, and then we'll show how we get the same result even rewriting it. So part A, given P of t equals 10,000 times 2 to the negative 0.4 t, write the rule for the function using base e. So we want to rewrite this function so that instead of that base of 2, we have a base of e. How would we do that? Well, we use that conversion that we just learned. We learned that b to any power is equal to e to the natural log of b times that power. So this base was 2. So I get to write this as e to the natural log of 2 times that power up there. So the way we get to rewrite it is instead of having 2 to that power, we have e to the natural log of 2, and then that power is still being multiplied up on top. And we can rewrite this a little bit. It's going to be approximate because natural log of 2 times the negative 0.4 is kind of ugly. I'm just going to round it a little bit to 5 decimal places. And I get 10,000 times e to the negative 0.27726 t. So this is my same function as what I have up here, just rewritten with base e instead of base 2. And those look very, very different, but they actually are going to get us the same exact values. So in part B, we're going to show that we still get the same result. Find P of 10 for both forms of the function. So I'm going to use the original form first. P of 10 is equal to 10,000 times 2 to the negative 0.4 times 10. That's equal to 10,000 times 2 to the negative 4 power. And when I type that into my calculator, I get 625. Now let's see if P of 10 is still 625 using the other form. It should be. So using the other form, we have 10,000 e to the negative 0.27726 times 10. Which is the same thing as 10,000 e to the negative 2.7726. And when you type that into your calculator, you get that it's approximately equal to 624.99 something, which is about 625. Now, the only reason we didn't get exactly 625 using that other form is, remember, we rounded this to 5 decimal places. So it's going to be a tiny bit off, but not very much. If we used the whole actual form, which had that natural log of 2 still in it, we would get exactly 625. But this is close enough. So that's just to show you how you could rewrite using a base of e if you don't have a base of e to begin with. So it looks like we have 2 examples left. We're going to do an example involving half-life, and then we're going to do a logistic population growth example, and then that will be it. So let's do the half-life problem. So carbon-14 has a half-life of 5,730 years. We want to write a model of the form Q of t equals Q0 e to the negative kt to represent the amount of carbon-14 remaining after t years. So what we're doing here is using the half-life of carbon-14 to write an equation that will help us figure out how old an object is based on how much carbon-14 it still has in it. This is called carbon dating. So we have to first figure out how to write this formula. I have Q of t equals Q0 e to the negative kt. And really, it looks like I don't have a lot of information in this problem. The only number that I'm given is this 5,730 years. That is t. And the only other thing I have is that this is a half-life. They're not telling me how much carbon-14 I'm starting with, none of that. But that's okay because we know the definition of half-life. Remember, a half-life is the amount of time it takes for the amount of that material to be reduced by half. And what that means is that if I'm starting with Q0 grams of this carbon-14, then after 5,730 years, I should have half of that left. That means the left side of the equation is half of Q0. That looks kind of scary, but the very first thing we're going to do when we're trying to solve for this K is divide both sides by Q0. So that's going to end up canceling out. So when I divide both sides of the equation by Q0, I get 1/2 equals e to the negative 5,730k. To figure out what that k is, take a natural log of both sides. On that right side, we know that simplifies to negative 5,730k. So that means I can get k by dividing both sides by negative 5,730. That's the exact value of k, but if I round it to, I'm going to use 6 decimal places this time, just to be extra safe, I get 0.000121 for my k. Now that I know what k is, we can write the formula that represents the amount of carbon-14 after t years. It'll be whatever Q0 is times e to the negative k times t. So this is my function representing the amount of carbon left after t years. Now we're going to use this model to determine the age of a piece of wood that has 42% of its carbon-14 remaining. To the nearest 10 years. So I don't know how much carbon-14 this piece of wood started with, but I do know it has 42% of that original amount left. That means the left side of the equation is 42% of my original amount. And on the right side, I have my original amount times e to the negative 0.000121 t. And if I solve this for t, that will tell me the age of this piece of wood. The first thing we have to do is divide both sides by Q0. So it doesn't matter that we didn't know how much it had to begin with, because the Q0 ends up canceling out. So when I divide both sides by Q0, I get 0.42 equals e to the negative 0.000121 times t. Take the natural log of both sides. And then on that right side, my natural log and my exponential undo each other. So my right side is now just negative 0.000121 t. So to figure out how old this wood is, I just have to divide by that crazy decimal. And I get natural log of 0.42 divided by negative 0.000121 is equal to t. And now I just have to type that into my calculator to figure out how old this wood is. Now when I type that in, we get that this is approximately 7,169.426. So to the nearest 10 years, that's 7,170 years old. That's a pretty old piece of wood there. All right, so notice, even though some of these problems seemed a little more complicated, we still used just the same techniques that we used in the last video to solve these. All right, so to finish this video up, we have to talk about what a logistic growth model is and do an example using that. So a logistic growth model is a function of the form y equals c divided by 1 plus a e to the negative bt power, where a, b, and c are positive constants. So something that's interesting to note about these logistic models, I could rewrite it in a different way, because we know what negative exponents do. So this could be written as y equals c over 1 plus a divided by e to the bt power, because negative exponents flip things to the bottom of a fraction. Now, why is this interesting? Well, think about what happens with our t. As t gets bigger and bigger and bigger and bigger, this exponential in this denominator is going to get huge. And so this constant a divided by a really huge thing is going to get really, really tiny. When you have a number divided by something huge, it ends up going to 0. Just think about cutting a pizza up. The more pieces you cut the pizza into, the smaller each piece gets. So this is like cutting a pizza into infinitely many pieces. They all disappear. What that means is as t gets bigger and bigger and bigger, this entire function gets closer and closer to this numerator, c. So as t gets bigger, our value y gets really, really close to c. And this c is called the limiting value. You're going to learn about limits very extensively once you're in calculus. This is like a very brief little intro to limits. So we're just saying as we plug in bigger and bigger numbers, we're going to get closer and closer to that value of c. The reason why we like that is because these models actually end up being very good at representing population. Now you might be wondering, but we already represented population with an exponential growth model. And that is true. And that works for small values of t. The problem with the exponential growth model that we were using before is it allows populations to grow forever. And we know that's not practical. In the real world, we have restrictions on our population size because we have resources that we would use up if we had too many people. So a logistic growth model is used to represent population growth where the population will eventually stabilize. It won't go beyond a certain limit because there won't be enough resources anymore at that point. Let's do an example using one of these logistic models. The population of California in millions can be approximated by P of t equals 95.2 divided by 1 plus 1.8 e to the negative 0.018 t, where t is the number of years since 2000. So notice this is one of our logistic models. I have a constant over 1 plus constant times e to a negative constant times t. That fits our logistic model. First thing we're going to answer for this is determine the population in 2000. Well, I have the model representing the population. I just need to know what to plug into it. 2000 is 0 years since 2000. So I need to plug in P of 0. P of 0 is equal to 95.2 divided by 1 plus 1.8 times e to the negative 0.018 times 0 power. So let's take a look at this. The exponent on my e ends up being 0. And we know e to the 0 is 1. So this is really saying P of 0 equals 95.2 over 1 plus 1.8, which is 2.8. And now I just have to divide that. And I get that the population in 2000 was equal to 34 million. Part B, how long will it take the population to double from its 2000 population? So my population in 2000, we just calculated, was 34 million. We want to know how long it's going to take to double. Double 34 million and you get 68 million. So we want to find out when our equation equals 68. So I would get 68 for the left-hand side equals 95.2 over 1 plus 1.8 e to the negative 0.018 t. So just a note, if you need it, that 68 is double my population of 34. So I have to solve this for t to figure out when this occurs. To do that, I'm going to multiply both sides by the denominator. So I get 68 times that denominator equals 95.2. And rather than distributing, I'm just going to divide both sides by 68. When I divide by 68, I get 1 plus 1.8 e to the negative 0.018 t is equal to 95.2 divided by 68, which is 1.4. Now I subtract 1 from both sides. And divide both sides by 1.8. So I get that my exponential is equal to 0.4 divided by 1.8. And now we're ready to take natural logs. Take a natural log of both sides. And then remember that the natural log and the natural exponential function undo each other. So I just get that negative 0.018 t equals natural log of that 0.4 over 1.8. So my t is just equal to that natural log divided by negative 0.018. If you type that into the calculator, you get that this is approximately 83.6 years. So it'll take about 83.6 years for that population to double and reach that 68 million point. Now the last part of this question is, what is the limiting value for the population of California? What this is saying is, as time continues to go on, what is the population going to level off at? When's it going to stop growing? And to do that, we just need to look at the original equation. Remember, our original equation looked like this. 95.2 over 1 plus 1.8 e to the negative 0.018 t. And remember, we said that the limiting value of a logistic equation like this ends up being the numerator. So that numerator, 95.2 million, is the limiting value of the population. That population of California is not going to exceed this value, provided our model is actually correct. If you want to see that in action, try plugging in very large values of t into that equation using your calculator. Plug in really huge values. Start with 100, maybe try 1,000. Just plug in bigger and bigger values, and you're going to get numbers that get closer and closer to this 95.2. All right, so that's it for today. That was a lot of word problems, I know, but our exponential and logarithmic equations are used a lot with real-world modeling. They come in very handy and can model lots of different situations. If you have any questions, feel free to drop them below. If you're a current student, you can also email or come to office hours, and I'd be more than happy to help. And I'll see you guys next time.